Hello everyone, and welcome to our channel, Mootechie. It's wonderful to have you here as we dive into a fundamental topic in biochemistry, pH and its measurement. I'm excited to guide you through this fascinating subject. Let's begin by exploring the very origin of the term pH. The acidity or alkalinity of a solution is determined by the number of hydrogen ions, or H+ ions it contains. For pure water, this number is 0.000000001 moles per liter. Now, if we take the logarithm of that concentration, we get the logarithm of 10 to the power of -7, which equals -7. But pH is actually defined as the negative logarithm of the hydrogen ion concentration. So, applying that, we get negative log of 10 to the -7, which is -7. Giving us a pH of 7. This is where we get the term pH, which stands for the power of hydrogen. This concept forms the basis of the entire pH scale, which ranges from acidic to alkaline. Now let's move on to how we actually determine pH. There are a couple of common methods. We can use simple indicators like litmus paper or more versatile pH paper that changes color. For more precise and accurate measurements, we use instruments like colorimeters or most commonly, pH meters. Next, we explore a bit of the history behind this essential tool. The modern pH meter was invented by a brilliant man named Arnold Orville Beckmann, who lived from 1900 to 2004. His invention revolutionized how we measure acidity and alkalinity. Coming up, we'll discuss the different types of pH meters available. You have handheld pH meters, which are portable and convenient. There are benchtop pH meters, which are more stable and often used in laboratories. And finally, there are continuous inline pH meters used for constant monitoring in industrial processes. Let us now look at the heart of these devices, the pH electrode. There are different kinds, like the separate glass electrode and reference electrode. But a very common type is the combination electrode, which conveniently houses both in a single body. You might also hear about a 3-in-1 electrode, which integrates even more functions. To understand this better, let's zoom in on the glass electrode. Its key part is a special glass membrane at the tip. Inside, there is an inner buffer solution and a leadoff element. The entire assembly is often shielded. This glass electrode is the sensitive part that actually detects the hydrogen ions in the solution you're testing. Following this, you'll notice the reference electrode is just as important. It has a porous ceramic junction that allows slow contact with the test solution. It's filled with an electrolyte solution and contains a reference element, like a wire. There's usually a refilled opening to maintain the electrolyte level. The electrolyte needs to be inert, have a high ion concentration for low electrical resistance, and it must be in contact with the measuring solution. Popular systems for the reference element include mercury with calomel or silver with silver chloride. Now let's bring these two parts together in the combination electrode. This clever design combines the glass membrane and inner buffer of the measuring electrode with the reference element and its electrolyte all in one single sturdy probe. This makes it very easy to use. So how does it all work? The fundamental principle is that the potential or voltage of the glass electrode is measured against the stable potential of the reference electrode. This relationship is described by the Nernst equation. The equation is E equals E0 plus 2.303 RT over NF times the log of the hydrogen ion activity. E0 is the standard potential when the hydrogen ion activity is 1 mole per liter. The part of the equation with the temperature variables gives us the Nernst potential, or the slope factor, which is the change in potential per pH unit. This slope actually depends on the absolute temperature of the solution. To visualize this, imagine the glass membrane in an acidic solution. The potential developed, E glass, is equal to E0 minus the slope factor, S, times the difference between the external pH and the internal pH. The internal buffer keeps the hydrogen ion concentration constant, so the change is all about what happens on the outside of that special glass membrane. Let's get an even closer look at the membrane itself. The glass is made of silicon dioxide with lithium ions embedded in it. It forms an inner gel layer and an outer gel layer. The inner buffer keeps the hydrogen ion level constant on the inside. When this membrane comes into contact with a measuring solution, the hydrogen ions in that solution interact with the outer gel layer, swapping places with some of the lithium ions. It's this ion exchange across the membrane that generates the electrical potential we measure. Of course, for accurate readings, we must calibrate the pH meter. The idea is that when the measuring and reference electrodes are placed in a solution with a pH of 7, the output should be 0 millivolts. However, several factors can cause this potential to drift over time. These include contamination of the reference electrolyte, evaporation or depletion of that electrolyte, chemical attack on the silver-silver chloride wire, something called junction potential, and the general aging of the measuring electrode itself. We correct for these drifts through calibration. We adjust the meter's reading so that it correctly interprets the millivolt output. For instance, before calibration, the meter might read a certain potential for a pH 7 buffer, but after calibration, we tell the meter that this point is exactly pH 7, and we also set the correct slope, which is typically around 59.2 millivolts per pH unit at 25 degrees Celsius. We typically perform a 2-point calibration using 2 different buffer solutions, or sometimes a multi-point calibration for even higher accuracy. This process ensures the meter's internal calibration curve is perfectly aligned. Now, even with a calibrated meter, we can encounter errors. In very alkaline solutions, the glass membrane can respond to other ions, like sodium, causing an alkaline error. Similarly, in very strong acidic solutions, an acidic error can occur. Errors can also arise from the reactivity of the reference electrolyte, or very commonly from variations in temperature. This brings us to a crucial feature, temperature compensation. The pH of a solution can actually change with temperature. For example, a 0.001 molar hydrochloric acid solution has a pH of 3.00 at both 20 and 30 degrees Celsius. But the pH of a different solution might change from 11.17 at 20 degrees to 10.83 at 30 degrees. There's a general rule of thumb, a 0.003 pH error per pH unit per degree Celsius. This is why modern meters have ATC, or automated temperature compensation. ATC adjusts the reading in real time to account for the current solution temperature, correcting for what would otherwise be an error at the theoretical isothermal intersection point. To keep your electrode accurate and lasting a long time, proper maintenance and storage are key. The glass electrode can be damaged by dehydration, which strips its vital gel layer. Other detrimental factors include chemical attack, freezing, extreme heat, and mechanical shock. Always store your electrode at ambient temperatures between 10 and 30 degrees Celsius with its protective cap on. The ideal storage solution for most combination electrodes is a 3 to 3.5 molar potassium chloride solution, which keeps the glass hydrated and the reference junction functioning properly. Finally, let's talk about a subtle but important point. The definition of pH is actually a bit of a misnomer. pH is not the negative logarithm of hydrogen ion concentration, but rather the negative logarithm of hydrogen ion activity. Activity depends on the ionic strength of the solution. The formula is pH equals negative log of the hydrogen ion concentration multiplied by its activity coefficient, F. This activity coefficient changes with the total molality of the solution. For example, at a molality of 0.01, the coefficient is 0.901. So the pH of a 0.01 molar HCl solution is not 2.00, but negative log of 0.01 times 0.901, which is 2.04. If we add more ions like 0.09 molar KCl, the coefficient drops to 0.829 and the pH becomes 2.08. So, to be precise, pH is the negative logarithm of the hydrogen ion activity in a solution. And that brings us to the end of our session on pH. Thank you. See you in the next class.